This is Rosen, section 9.3 on primes and greatest common divisors. Here we encounter the concept of writing greatest common divisors as a linear combination of the two integers in question. This is known as Bezout's theorem. We don't prove it here, but if we have a and b positive integers, then we are able to write the greatest common divisor as a linear combination of those two integers with integer coefficients s and t. And if we do write the greatest common divisor as a linear of a and b as a linear combination of a and b, s and t are called the Bezout coefficients of a and b, and the equality is called Bezout's identity. Here's a quick example of the fact that we can do this. Greatest common divisor of 6 and 14 is 2, and we can write 2 as 1 times 14 minus 2 times 6. And the way we're going to ultimately find Bezout coefficients is by a repeated application of the Euclidean algorithm, with back substitution, which I will do next. Here we want to find the greatest common divisor of 252 and 198. So we set up the division algorithm as 252 equals 1 times 198 plus 54. Then 198 becomes 3 times 54 plus 36. And we're doing this because we need to find the greatest common divisor, right? And then 54 is equal to 1 times 36 plus 18. And 36 is equal to 2 times 18 plus 0, which are stopping condition. So 18 is our greatest common divisor. And we want to express as a linear combination of 252 and 198. So we'll start there and we'll reverse the equality. And we'll say 18 is equal to 50, that's equals 54 minus 36. And then we'll substitute for each remainder successively till we get back up to the top. That's equal to 54 minus 198 minus 3 times 54. And that's equal to 4 times 54 minus 198. And now we substitute for 54. 4 times 252 minus 198 equals 4 times 252 minus 5 times 198. So my Bezout coefficients are 4 and negative 5 for 252 and 198 respectively, having a greatest common divisor of 18. I have this built out on this slide here, which you can see in your notes, but I wanted you to see it done by hand so that you could see this two-pass method. There's a single-pass method, which I don't teach. I do ask that you know the two-pass method for exams. Consequences. If limit 2 is if I've got a, b, and c positive integers such that the greatest common divisor of a and b is 1, and I know that a divides b times c, then I can conclude that a divides c. Here's the proof. So assume the greatest common divisor of a and b is 1, a divides b times c. By Bezout's theorem, 1 can be expressed as the linear combination of a and b with integers s and t. If I multiply both sides by c, I get this expression here. Well, SAC is clearly divisible by a, but b times c is also divisible by a by assumption. And that means A must divide the sum, SAC plus TBC, and that means A must divide C. This lemma will state without proof that if P is prime and P divides A1 through the product of A1 through AN, that P must divide one of those factors. And we want to prove that the prime factorization of a number is unique on the next slide. So prove that the prime factorization of a positive integer is unique. Suppose that it is not unique. Suppose that it can be done as a product of primes in two distinct ways. So n is equal to P1 through PS product, and n is equal to Q1 through QT product. Now we set those two products equal to each other, and then we divide out any common primes that happen to be there. And the problem is that this first prime on the left must divide one of these primes on the right by the lemma 3, but we've already assumed that they are distinct primes, and so we reach a contradiction. That means there can be only at most one factorization of n into primes. Finally, earlier when we discussed congruences in this chapter, we had noted you can't necessarily divide by a common factor integer on both sides of the congruence and maintain it. However, if you divide by an integer relatively prime to the modulus, we retain the validity of the congruence. So here's our theorem. If I have AC is congruent to BC mod M, and the greatest common divisor of C and M is 1, then I can conclude that A is congruent to B mod M. In other words, I've effectively divided both sides by C. Here's the proof. Since AC is congruent to BC, that means M divides AC minus BC. That means M divides either C or A minus B, but we had assumed that greatest common divisor of C and M is 1. Therefore, by that earlier lemma, M must divide A minus B, which is the definition of congruence of A and B mod M. And that is the use of Bezout's theorem to find Bezout coefficients and some of the benefits of doing so.